All right, here's part 2 of 4.9. We're going to look at initial conditions and particular solutions. This is where we can find the actual value of the constant at the end of our antiderivative. So an equation that involves the derivatives of a function is called the differential equation. If I asked you to find me the antiderivative equation, capital F of x, of dy over dx equals 3x squared minus 1, you would give me a general solution. Okay, so we're going to add 1 to the 2, make it x cubed, then divide it by 3. Multiplying that to the 3 will cancel out to x cubed. Minus 1, we just multiply that by an x. That gives me minus x, and we add our c. So this is, again, your general solution because we don't know what c is. However, what if you know that f of x passes through the point 2, 4? Then f of 2 is equal to 4. So you can put 2 in for all the x's and set this equal to 4 and solve for c. So there's my substitution. I set it equal to 4. I'm going to get 8 minus 2 is going to be 6, plus my c is equal to 4. Subtract over the 6 to get negative 2. Move that in for the c, and now there is your particular solution. Again, this is only going to work if you have some initial conditions, like knowing what points are on your antiderivative function. All right, example 4. Let's try this one. Find f if f prime of x is equal to e to the x plus 20 times 1 plus x to the negative 1 power, and f of 0 is equal to negative 2. All right, well, e to the x, this will be straightforward because remember, when I take the derivative of e to the x, it's still e to the x, so that's not going to change when I do its antiderivative. But here, we're going to move this into the denominator, get rid of the negative exponent, because whenever I see that 1 plus x squared, I think of that special derivative for the inverse tangent of x. So if we're going to go right to left, take the antiderivative, this is going to equal the inverse tangent of x. So like we said, e to the x wouldn't change, plus 20 times inverse tangent, of x plus c. So f of 0, we'll put in zeros. E to the 0, that will be a 1. Inverse tangent of 0, that's going to be a 0. So 20 times 0 is 0, so we're setting this equal to negative 2 because we know this value of f of 0 is equal to negative 2. Subtract over the 1, c equals negative 3, and we'll plug it in for c. And now there is my new function that is now a particular solution because we were able to find negative 3 for our c. All right, b. Find f, the double derivative. So now we got to do the antiderivative twice. Double derivative f of x equals 12x squared plus 6x minus 4. F of 0 is equal to 4, and f of 1 is equal to 1. All right, so let's get started here. Put our powers on our variables, put parentheses after our coefficients, and now let's take the antiderivatives of our variables. Add 1 to the 2, make it 3, divide by 3, x to the third over 3. Add 1 to the 1 makes it a 2, divide x squared by 2. Put it in your parentheses. It's a constant, just multiply it by x. Let's do some simplifying. 3 goes into 12, 4, 2 goes into 6, 3, and there's my f prime, my antiderivative of f double prime, and don't forget we got to put in our plus c because now we got to do the antiderivative of this because we have to get to f so we can plug in these values. So again, 4 times parentheses plus 3 times parentheses minus 4 times parentheses plus c times parentheses plus a new constant, we'll call it capital D. So x to the third, add 1, divide by 4. 3 plus 1 is 4, so x to the fourth over 4. X squared, add 1, make it 3, divide by 3, x cubed over 3. X to the first now becomes x squared divided by 2, and c gets multiplied by x. Cancel, cancel, simplify. We have f of x equals x to the fourth plus x cubed minus 2x squared plus cx plus d. Oh, wait a minute. That's the y-intercept, 0, 4. Because if I put 0 into all those x's, That's going to cancel that out, and that's going to leave d equal to 4. Done. All right, so we'll have to use f of 1 equal to 1 to find the c value. So we're going to put in all these ones, 1 to the 4th, 1 to the 3rd, minus 2 times 1 squared plus c times 1. Well, that's just all 1, so 1 plus 1 is 2. Minus 2, that's canceled. So c plus 4 equals 1, subtract over the 4, c equals negative 3. Put that in for c up here. Oh, I'm sorry, right here, because we already put the 4 in. For c is going to be minus 3x, and there is your particular solution for f of x. All right, there's our antiderivatives. Come on, mouse. I tell you, this thing's getting too sensitive. Okay. Rectilinear motion. Antidifferentiation is particularly useful in analyzing the motion of an object moving in a straight line. We know if the object has position function s equals f of t, then the velocity function is v of t equals s prime of t. This means that the position function is an antiderivative of the velocity function, and we can go right down the line. Likewise, the acceleration function is a of t equals v prime of t, so the velocity function is an antiderivative of the acceleration function. If the acceleration and initial values s of 0 and v of 0 are known, then the position function can be found by anti-differentiating twice, very similar to like we did in the last problem. All right, so example 5, a particle, there we go, moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v sub 0 equals negative 6 centimeters per second, and its initial displacement is s of 0 equals 9. So basically they're giving us the y-intercepts. They're telling us what our c and d are going to be. Find its position function s of t. All right, let's start with their acceleration, and let's move that up to the velocity function. So that's going to be t to the first, that's going to be t squared divided by 2, so 3t squared plus 4t. Then add your c, put in your v sub 0, so that's going to be minus 6. There's our velocity function. Let's do the antiderivative of this to get to s of t. So 2 plus 1 is 3 for the power, divide by 3, that's going to cancel your 3, so t cubed. Put us 1 plus 1 is 2, so t squared over 2 reduces the 4, makes that 2t squared. Multiply the minus 6 by t and add on your d, your next constant variable. Again, s of 0, that's your y-intercept, so d is 9, and you found your position function. Very similar to what we did in the last problem. However, what was different in the last problem is that they gave us 2 values that went, if you will, the position function. They didn't give us something for the first derivative function and then finally our f of x. All right, so a ball is thrown upward with a speed of 64 feet per second from the edge of a cliff 80 feet above the ground. Find the height above the ground t seconds later. So that means we've got to find our function s of t. When does it reach its maximum height? So that we need the derivative, so we'll have to look at the velocity equation. And when does it hit the ground? We need our position function and set it equal to 0 and solve it for t. All right, so reminder, remember we talked about our velocity. If we're working in meters, it's 9.8 meters per second squared. But if it's in feet, which it is here, we're working with 32 feet per second squared. Okay, so to understand the problem a little better, remember the motion of the ball is vertical, so choose the positive direction to be upward. At time t, s of t represents the height above the ground, and the velocity of t is decreasing. Therefore, acceleration must be negative for a of t equals negative 32. So we're just starting with a constant. So let's find the velocity function. Just multiply that by t and add a z. There you go. There's v of t. Wait a minute. What was our velocity speed? It was 64 feet per second. So that's like saying at time 0, we threw the ball at 64 feet per second. That's time 0, so that's v of 0. So we'll put in 0. So that means c is going to be 64. Here's my velocity function, which means now I can tell you what time it reaches its maximum height by solving this for t by setting it equal to 0. That's going to be your critical number where you find your local max or mins. Because this is technically the first derivative of your standard, or your s of t, your position function. So let's set this equal to 0. And we solve it. So 32 minus 32t, add that over here, divide it over 64 over 32 is going to give me 2 seconds. So I'm going to reach the maximum height at 2 seconds. So if I actually wanted to find out what that is, I got to go find a position function, plug in a 2, and I'll tell you what the maximum height is. When does it hit the ground? We need our s of t. So taking your velocity function, t squared divided by 2 gives us negative 16t squared. Multiply 64 by t and add a d. To find d, we use the given height of 80 feet at s of 0. At time 0, you're 80 feet above the ground. So that means d is 80. Now we can find when does our ball hit the ground. Set this equal to 0 and solve for t. Wait a minute. 16 can go into 64, and 64 plus 16 is 80. So 16, let's divide everybody by a negative 16 to get a positive t squared. So t squared minus 4t minus 5 is equal to 0. This is going to factor. We're going to get t minus 5 and t plus 1 equal to 0. So t equals 5 and t equals wait a minute, you can't have negative time here. So we'll throw out the negative 1. That's not plausible here. So we hit the ground in 5 seconds. Sound good? All right, so that concludes 4.9 part 2. I'll get working on the next one for you.